Yes, hello, grade 10s. How are you doing today? My name is Patrick Kamala. I am a tutor and educator for mathematics and physical sciences, grades 10 to 12. Now, today I'm so happy to take you through these longitudinal waves. I know you're coming back on Monday, but if you want to pass, you don't need to have holidays, okay? Now, as we do this waves, please follow the worksheet on the group chat so that you will be up to date. Okay. Now, what are longitudinal waves? Longitudinal waves. Now, a longitudinal wave is a wave where the particles of the medium move parallel to the direction of propagation of the wave. What is it? I said it is a wave where the particles of the medium move parallel to the direction of propagation of the wave. Now, in this case, parallel means that the particles of the medium move back and forth. Okay. Now, these longitudinal waves, actually, we're going to look at them considering a spring. Now, if you have a spring, for example, let me draw for you one here. Like this one here, check this one here, and then this is spring. If you happen to push it forward and backwards, okay, then it's going to form a wave which is moving forward and backwards, okay. And now, such a wave is going to be moving in the direction of such particles of the spring. They're going to be moving in the direction of the wave. Okay. Now, as you're going to see shortly. Now, as we push from this side here, check. As we push from here and pull, we're going to generate waves in this spring here. Now, we have other terms which we have in these longitudinal waves. One of them is called compression. Now, what's a compression? What is a compression? Now, a compression is a region in a longitudinal wave where the particles are closest together. Check this out. You see these first particles here, they are very close. Here they are farther from each other. Okay. Now, this region where the particles are closest together is called what? A compression. Okay. And then what about a rarefaction? What about a rarefaction? Okay. Now, a rarefaction is a region in a longitudinal wave where the particles are farthest apart. Now, check this example here. Now, in this spring here, if you see properly here, you see that in here, these are too compressed, like they are too close together. What about starting from here? You can see these are further apart, okay, up here. Then they are compressed again. Then they are further apart again here. Then they are compressed here, and then further apart here. Now, what is causing this compression and the further apart of the spring particles is the movement of the wave. Now, if this wave is being pushed and pulled horizontally, it's going to form regions whereby we're going to have some of the particles compressed, others far from each other. Now, these particles where they are compressed too much, where they are closest together, like here and here and here, we call them what? Compressions. So compression means from here up here, and again also from here up here, and again also from here up to here. You see, now in these spaces, the spring or the medium particles are closest together, and we call them what? Compressions. Then where they are farthest apart, we call them rarefactions. Rarefactions. Let me explain this again. Now check from here. from here up to here, this region, you see the particles are farthest apart. So this is a rarefaction. Also note, from here up to here, the particles are farthest apart. It's also called what? A rarefaction region. Another one is also here. From here up to here, it's also called what? A rarefaction region. Let us proceed, guys. Let us proceed. Next. Now, a wavelength in a longitudinal wave is the distance between two consecutive points that are in phase. Listen again. What is wavelength? It is the distance between two consecutive points that are in phase. Now, with longitudinal, this refers to the distance between the two consecutive compressions or between two consecutive rarefactions. Now, remember we talked about the transverse waves, where we talked about the crests and the troughs, and we said that the wavelength is the distance between two consecutive crests and the two consecutive troughs. Now in this particular case, the compressions, they are like the crests in the transverse wave, and then the rarefactions, they are like the troughs in the transverse wave. So now the distance between two consecutive compressions is called what? A wavelength. Or between two consecutive rarefactions is called what? Wavelength, as you're going to see it shortly. Let us proceed. Now another one here is called amplitude. Now amplitude is the maximum displacement from equilibrium. Again, for a longitudinal wave, which is a pressure wave, this would be the maximum increase or decrease in pressure from the equilibrium pressure that is caused when a compression or a rarefaction passes a point. Now we're going to discuss some more about this. Don't worry about it for now. Let us proceed here. Now note something here. When I say points in phase, this is what I mean here exactly. Now look here, guys. Look at this spring here. A wave is moving through it. It is being moved, pushed forwards and backwards. And if our wave, for example, is moving to the right, like this one here, like this, okay. Now moving to the right, as we push and pull this spring here, we're going to generate waves, whereby in some regions we're going to have them, the wave particles being so close. Like check here, from here, from here up to here, you see the wave particles are so close. They are closest together. Another space where they are closest all together, we can see that also from here, check, also from here up to here, they also what? Closest together. Check another one also from here, check, from here up to here, they are also closest together. And also lastly, from here up to here, also what? Closest together. Now the regions where they are closest together, they are called what? We said they are called compressions. So this is a compression region, another compression region, and another compression region, and another compression region. Now we have other regions whereby the wave particles are farthest apart. Check from here. Check from here up to here. Check. Also from here. From here up to here, the particles are farthest apart. Also from here up to here, they also what? Farthest apart. Now listen carefully. If we say points are in phase on longitudinal wave, this is what you mean. Take an example of this compression region. Now the compression region starts from here. You see that? Now this compression region, the distance where it starts from, as you can see, it starts from here. Now look at the next compression region. it also starts from here. Check. Now the distance from where the compression starts, okay, to the next compression where it starts from is called one wavelength. That's why there's lambda here. This lambda is a Greek letter which represents one wavelength. Okay. Now check again. Also from the start of this compression here to the start of the next compression, it forms another what? Another wavelength. Again, also from the start of this other compression region here to the start of the next compression region forms another what? Another wavelength. Now we can also use rarefactions, and now this is our rarefaction here. If you check here, actually this is check. This is 1, 2, 3, 4, 5. Now these are the 5 particles which comprise of the rarefaction region. Now if you come here, also you can see this is 1, 2, 3, 4, 5. So this is another region for the rarefactions. Also here note 1, 2, 3, 4, 5. Another rarefaction region. Now note something. Now from the center of this first rarefaction to the center of the next rarefaction is also one wavelength. Also from the center of the second rarefaction to the center of the last rarefaction is also another what? Another wavelength. In other words, these points, they are in phase. They are in what? In phase. Hope we are together. Okay. Now so don't forget that a wavelength is the distance between two consecutive points in phase. That means from one particular point in for example in the compressions, like the start or the end, to the next point in another compression is one wavelength. Hope you understand, guys. Let us proceed. If you don't, please inbox me. Okay, now another definition is period of a wave is the time taken in seconds by the wave to move one wavelength, and the period is equals to 1 over frequency. Likewise, frequency of a wave is the number of wavelengths per second passing a fixed point, and the frequency equals to 1 over time, t. This t is the periodic time which is here. Actually, frequency and the periodic time, they are inversely proportional to one another. They are inverses of each other. Okay. Now another definition is wave speed. Is the distance a wave travels per unit time. What is wave speed? The distance a wave travels per unit time. Now wave speed is measured in meters per second, and the formula is given by V, that's wave speed, equals distance traveled divided by time taken. Now this distance is this distance traveled in the wavelength, and like this is lambda over time taken, periodic time. Now however, our frequency is the same as 1 over t. So if I take this again and I say that from here you see V equals to lambda over t, so I can write it as lambda times 1 over t. But what is 1 over t? 1 over t is actually what? 1 over t, this 1 over t here, it is the same as frequency. The same as what? Frequency. Check, frequency equals 1 over t. So it means that where I have frequency 1 over t, I can put frequency and I get my formula as lambda times what? Times frequency. So in other words, the speed of the wave v equals to frequency times the wavelength in meters. Frequency is measured in hertz. What about wavelength? In meters. So don't forget this formula because I'm going to use it too much. So the speed v of a wave is given by what? By the frequency multiplied by what? Multiplied by the wavelength, which is lambda in meters. Frequency must be in hertz, What about wavelength? Must be in meters. That's called the wave equation. Okay, let us proceed. Next page. We take example 1. They say that a longitudinal wave, okay, they say what? They say that a longitudinal wave has a compression distance of 10 meters. It takes, they say, it takes the wave 5 seconds to pass a fixed point. What is the wavelength of the longitudinal wave? Read the question again. They said that a longitudinal wave has a compression distance of what? Of 10 meters. Then they say it takes the wave 5 seconds to pass a fixed point. They say what is the wavelength of the longitudinal wave? Okay, let us check what they have given us, guys. Let us see what we have here. Now, what have they given us? They have given us that a compression to compression distance. Note that from one compression to what? To another compression. Distance is what? Distance is 10 meters. Now the question says that they also say that it takes the wave 5 seconds to pass a fixed point. Now they say what's the wavelength of the longitudinal wave? What is what? The wavelength of the longitudinal wave. Now what do you think here, guys? I don't want rhyme work, but we said that wavelength is the distance between two consecutive points in phase. And we said that such points can be from one compression to another, or from one rarefaction to another. Okay, now let us try something here. Let us see how we get the answer here. So they said from one compression to another compression, 10 meters. Let us check it out here. So notice on here, I'm gonna try to draw this wave here. Okay, so if this is my compression here, let me do like this. Let me draw it here. I'm starting from here. Okay, let me make it a little bit thicker. Okay, you see. Now if this is my first compression region, okay, and then after the compression region there comes what? A rarefaction. Now this is rarefaction here, this is rarefaction here, this is a rarefaction region. Okay, this is a rarefaction region here, guys. As you can see, the particles are far from each other. Then there comes another compression region here, another compression region. Okay, we are still in the compression region here, and then we can continue with another rarefaction. Okay, another rarefaction here. Okay, let us now analyze the situation. Now if you see what we have here, you can see that I have my distances. They say it has a compression to compression, so I can take the start of this compression here. My compression starts from here, right? Starts from here, and they say compression to compression, so to another compression which is also starts from here. Okay, check this out. Okay, now if I look at my distance between the starting point of this compression and the starting point of the next compression, anybody who remembers, what did we say? What does that represent? What does that show us? We say from here up to here. Do you remember, guys? Talk to me now. The distance from the start of one compression to the start of the other compression, we said is what? Talk to me, please. You said it's called lambda. So this is my wavelength. In other words, my wavelength is 10 meters. Because they said from compression to compression is what is 10 meters. So my answer here is what? It is 10 meters. It is 10 what? 10 meters. That's my answer. 10 what? 10 meters. From one compression to the next. Okay, now they say, what is the speed of the wave? What is the speed of the wave? Now this wave here, they said that it does what? They said that it takes the wave 5 seconds to pass a fixed point. Did you hear that? It takes what? It takes the wave 5 seconds to pass a fixed point. What does that represent? 5 seconds to pass a fixed point. And that's the time taken for one complete wave. Now the time taken for one complete wave to pass a fixed point is called what, guys? Talk to me. We said it is called what? It's called periodic time. So this is my periodic time here. This is my periodic time, T. Okay, what does the question want? The speed of the wave. But we said that V equals to what? Equals to the frequency, okay, multiplied by what? By the wavelength. Okay, now in this particular case, we know that the frequency is the same as what? The same as 1 over T, whereby T is the periodic time, okay? Then times what? Times the wavelength. Times what's our wavelength here? It is lambda. And what is its value? Anybody who remembers? So we're going to have 1 over T. What is my T? My T, we have seen it is what? It is 5 seconds. I'm going to say 1 over 5. Okay, 1 over 5. Then multiplied by what? Multiplied by the lambda, which lambda was 10. So times 10 here, times 10 here. Which answer do I get here? So 10 divided by 5 gives me what? Gives me 2. So it's going to be 2 meters per second. That'll be 2 what? 2 meters per second. So that's the speed of this wave. It is what? It is 2 meters per second. I hope you understand, guys. Let us proceed. Next example says here that we'll take example 2. They said that a flute produces a musical sound traveling at a speed of what? 320 meters per second. The frequency of the note is what? Is 256 Hz. Calculate the period of the note and the wavelength of this note. Okay, let's check it out properly. Let us understand what we know. What have they given us here? They are saying that a flute produces a musical sound traveling at a speed of 320 meters per second. So we know the speed of this. The speed is what? It is 320 meters per second. They said the frequency of the note is what? It is 256 Hz. So we know the frequency. How much is it? It is 256 Hz. Okay? It is 256 Hz. Calculate the period of the note. We're looking for the period of the note. Okay? Now, what do we know? How do we find the period? The period of the note, the period T equals to what? Talk to me. Period T equals to 1 over the frequency. 1 over what? 1 over the frequency. But what is our frequency here, which they gave us? 256. So if I divide 1 by 256, what do I get, guys? 1 divided by 256. What's my answer? Let's check it out. 1 divided by 256. What's our answer? 1 divided by 256. Now here I'm going to have 256. Okay, 1, take 1 divided by 2, 5, 6 equals to, yeah, that is 3,91 times 10 to the power negative 3. Okay, 3,91 times what? Times 10 to the power negative 3. Okay, so that is 3,91 exponent negative 3. 3,91 3, 9, 1 times 10 power negative 3. So this is my answer for the what? For the period. Okay, seconds, ne? Seconds. Okay. Next they say the wavelength of the note. Now I'm looking for the wavelength now. What is the symbol for the wavelength? Anybody who remembers? Symbol for wavelength is what? It is lambda. Okay, so what do I do here to get my wavelength? Now I know that there is a formula which is called the wave equation, which we discussed now, and that formula says what? It says that the speed of the wave, that is v, equals to lambda multiplied by what? By the frequency. Okay, so if you check what we have now, so far we know something. We know the speed, that is 320, and looking for the wavelength lambda, we know the frequency, so we can substitute these guys. We can do what? I'm gonna say 320, okay, equals to what? Equals to lambda multiplied by what? By the frequency, which is what? Which is 3,913,91, then times 10 to the power negative 3. Okay, so now talk to me, how do I get my lambda from here? I divide both sides by what? By 3,91 exponent negative 3. So I'm gonna say that my lambda is gonna be what? So lambda will be given by the 320, 320 divided by what? Divided by 3,913,91 times what? Times 10 to the power negative 3 times 10 to the power negative 3. Okay, let's check it out now. 320 divided by 3,91 times 10 to the power negative 3. What's our answer? 320. So 320. Okay, 320. So it's gonna be 320 divided by 3,91 times 10 to the power negative 3. That means exponent negative 3. Negative 3. What do we get? Okay, it gives us what? It gives us 81841,43. 81841. 81841. 81841. 81841. Okay, so we get what? 81, then 841. Comma what? Let's check it again. Comma was our answer, comma 43, comma 43, comma 43, comma 43. Now this is our wavelength, which must be in what? In meters. Okay, hope we are together, guys. Don't forget what I did. I first found my periodic time, and then I used it, and then I used V equals to lambda times frequency, whereby I did what? I did something else. I did substitute. Let me check it out again. Oh no. This is T. This is T here, and I was looking for what? For the frequency. No. So what's my frequency? The frequency was given to me. The frequency was what? It was 256 Hz. Oh my God. 256 Hz. I beg your pardon. 256 Hz. 256 Hz. 256 Hz. Okay, so it's supposed to be 256 instead of what? Of this. Okay, so I'm going to divide it by what? By 256. Divided by what? By 256. Divided by 256. Divided by 256. Okay, so it's going to be 256 here. 256. 256. Okay, now what do you get here? It's going to be 320 divided by 256. 320 divided by 256. 320 divided by 256. 320 divided by 256 equals to 1,25 meters. 1,25 meters. 1,25 what? 1,25 meters. 1,25 meters. So this is our wavelength. I beg your pardon, guys. This was not supposed to be what? 256. 256. 256. Okay. Let us proceed. Let's continue here. Let's proceed. Now, next, what do we have? So that brings us to a type of longitudinal which is called sound wave. Now, what are sound waves? What's a sound wave? What is a sound wave? Now, a sound wave is a longitudinal wave in which the particles of the medium move backwards and forwards in the direction part of the what? Direction in which the sound wave travels. Now, under sound waves, we look at the pitch, loudness, and the quality. Okay. Now, the pitch is how high or how low sound is. So, in other words, if you talk about pitch, it means how high or how low the sound is. Okay. So the human ear perceives pitch as frequency. That is to say, the higher the pitch, the higher the frequency. So in our physics here, if you hear the word pitch related to frequency, because they are proportional to each other. In other words, the higher the frequency, the higher the pitch. Okay. And then loudness of a sound is the ear's perception of the intensity of the sound. Now, loudness depends on both the amplitude of a sound wave and its frequency. So, we know what? Loudness goes hand in hand with amplitude, meaning the higher the amplitude, the higher the loudness. The louder the what? The sound. And the lower the amplitude, it means what? It means the softer the sound. It won't be loud. Okay. Alright, it has I have said pitch related to the frequency, loudness related to what? To the amplitude. Okay. Let us proceed then. Work example 3. Choose an item from column B that best matches description in column A. Write only the letter next to the question number. Okay, so here they say column A, we have the sound that a female singer produces when she sings. Now, this question is relative, but under normal circumstances, a female singer produces which sound here? What happens here? There's frequency, there is pitch, there is low pitch, loudness, whisper, and then high pitch. Now, the female singer produces what? Talk to me. The female singer produces a high pitch, so that is F. So number one here is what? Number one is F. Number one is F, okay. And then number one is F, guys, not F. Number one is F. And then what about number 2? Number 2 says what? It says that used to measure pitch. Now pitch, like I said before, we always relate it to what? The frequency. So frequency is part A in column B, so number 2 is A. Number 2 is A here. And then number 3, it says a sound wave with very small amplitude. With very small amplitude, so what is it going to be? It's going to be low pitch, loudness, whisper, high pitch. So because of the saying that it is a very small amplitude, it must be a whisper. Hello, 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 hello. A whisper, eh? So whisper is E, so you're going to have E here. You're going to have E here. That's for a whisper because of the low amplitude, okay. And then number 4 says the sound that a male singer produces when he sings. Hello, 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 hello. Now, a male singer, it's called a low pitch. A low pitch, that is C. That is C. And then number 5, related to the amplitude. Now, amplitude relates to what? Anybody who remembers? Amplitude relates to the pitch, guys. So pitch is B. Pitch is what? Pitch is B. Pitch is B. So number 5 is B here. They say related to the amplitude. Okay. So this is B here. And then next, a human ear's perception of frequency. A human ear's perception of frequency. What is it? Now, a human ear's perception of frequency. Okay. Let's check it out again. Now we said that frequency goes hand in hand with the pitch, right? What about loudness? It goes with amplitude. Okay, so it means that a human ear's perception of frequency, it must be what now? Talk to me. It must be the pitch. So this must be pitch here. I beg your pardon. This must be pitch. Pitch is B. Pitch is B here. Okay. And then so this is not supposed to be B here. Let us remove it. It's not correct here. And then let's check this again on one more time. What do we have here? They said that okay, one more time. Let's check it out again. Make it smaller. Okay, now they said that they said that used to measure the pitch. Now pitch goes with frequency. That was what? That was A. That's frequency. Then number 3, a sound wave with very small amplitude. That will be a whisper, which is E, and then the sound that a male singer produces when he sings, that is a low pitch, which is C, and then related to the amplitude. Now amplitude relates to the what? To the pitch. So pitch is B. Pitch is also B here. Then loudness goes hand in hand with amplitude. No amplitude this side. Oh yeah, so this must be B again. This must be what? It must be, what they're saying, related to the amplitude. Amplitude. Okay, that's number 5. Amplitude also goes with loudness. So yeah, so it is D here. This is D. This is D here, which is loudness goes with amplitude. Okay, let us proceed, guys. Let us proceed. Next, we take example 4. Study the following diagram representing a musical note. Redraw the diagram for a note with a higher pitch that is louder, that is softer. Just previously, did we finish it? Or let me take one more time. Yeah, I think it was done. Yes. Okay. Another example here says that they study the following diagram, and then read the diagram for a note with a higher pitch. Okay, now we want something here with a higher pitch. We see that pitch goes hand in hand with what? With frequency, right? So if you take here, guys, how many waves are here? This is 1 up to here. Okay, so this is my first wavelength. It stops here. That means from here, check from here up to here. That's the first wavelength. Another is going to be here. Okay, so these are 2 wavelengths. So because I want to have a higher pitch, I must have many wavelengths from here up to here. So what must I do? I'm going to draw something like this. They must be many. So I can, these are already 2. These are 2 here. So I'm going to draw here. Let's check this out. I'm going to try this. Okay, it's going to come here like this. Okay. Okay. All right, let's check the how many are they now. Let me use the blue color now. Check. Now from this point here up here is 1 wavelength. Also from here up here is another wavelength. Also from here up to here is another wavelength. So now instead of having only 2, there are 3. So it means that this one in the red is going to be having a higher pitch. Okay, now 4.2 they say that is louder. So being louder means it must be having a higher amplitude. A higher amplitude. So we're gonna draw it here with a higher amplitude. Okay, here we go. It means now must be higher than this one here, maybe passing here. Okay, check that now. Then it gets here, must be higher than that. Then even here, higher than this one here again. Okay, then here higher than this other amplitude. and then it's over the same time. Yeah. Now that one has got a higher amplitude, and hence it's gonna be what? It is louder than the other one. Okay. Then they say that it's softer. Now to get a soft sound here, it must be of a low amplitude. It must be of what? A low amplitude. Check it out. Maybe like this one here. Starting from here, like this, lower, but passing the same point. When here lower, when here lower, when here lower, and stopping there. Now this is a softer sound. Okay. Hope we are together, guys. If you have any questions, please inbox me, and I'll get back to you. However, we have some questions to try out here. So this question here, try it out, please. If it is not clear here, check on the group chat. Check on the group chat. It's there. Try it out. Try it out. Try it out. And when you are done with this one here, try out the next one as well. This one here. Okay, by the way, these are comparisons, rather rarefactions, comparisons, rarefactions, comparisons, and then rarefactions. So don't get lost. Don't get lost. Okay. Try this as well. Okay. Yes, now this one is our next video.